Okay, welcome back to example number 7. What we're going to do is work out these problems by differentiation. So we're going to try to minimize or maximize this function, and clearly we want to maximize the area. We'd prefer not to minimize it. So what I'm going to do is find what is a prime of x. This function describes area. So if I graphed this guy out using, in fact, you know what? Let's go ahead and do that. So I'm going to pull up Desmos. Let's just take a look at our area function. And it's not a bad idea to go ahead and do things like this. So 250, as long as you're not relying on them. So 250x minus 1/2 x squared. Okay, so there's our function. Now you can tell it gets out of range very quickly. So what we're going to do is play around with the axis. So x is a length measurement, so we don't want that to be negative. So let's make it 0. And the maximum x could possibly be is 500. Okay. Now let's look at the y values. The y is the area. That's the up and down part. So our area, we know it can go at least up to 30,000. So let's say 50,000. Now we've got our curve set in here. What I want you to look at is on this curve, okay, along this curve like this, at each of these points is a different x value. So if x was 100, meaning if this length right here was 100, regardless of what this length is, of course we can compute it if this is 100, okay, but regardless of what this length is, at 100, over at 100, we have 20,000 meters squared. So we can go ahead and compute that. Okay, now again, we went through an example and we said, well, what if x was 300? Well, again, if x is 300, we go over to 300 and we go up, and it tells us that our area is 30,000. Okay, so this right here is the area as x changes. So to get to the top of it, what we want to know is, how does the area change with respect to x, and when is the change flat? So notice between here and here, as x increases, area increases. But over here, as x increases, area decreases. So by finding the derivative and setting it equal to 0, we're going to get this maximum up here. So that's what we're going to go ahead and do. Okay, so we need a prime. So that's going to be equal to 250 minus 2x, just like that. And now what we want is we want the derivative to equal 0, because that gives us, again, that gives us this piece right here. It'll give us this spot. Okay, so we'll go back, set this guy equal to 0. Okay, so we've got 250 is equal to 2x, or x is equal to 125. So let's go back. That doesn't look right. Let's see here. We have 250 minus, not 2x, sorry, just minus x when I take the derivative here. My fault, did that in my head wrong. 2 times a half is 1, not 2, so 1 times x is just x. Move this guy over, that means x is 250. Now that looks much better. So at 250, over here, at 250, in fact, let me just go ahead and see if I can't move it up a little bit. At 250, we are at our maximum, and our maximum area is somewhere right around here, so it's probably like 31,000 something. Now we can go ahead and calculate that. So the dimensions are, if this length here is 250, then this length is 250 minus a half of 250. And a half of 250 is 125. So this length would be 125. And if we go ahead and calculate the area at 250, we can plug in 250 here, or we can just take 250 times 125. And that gives us 31,250 meters squared. Okay. Now let's go ahead and look at problem number 2. So we had this picture, and we wanted to go ahead and minimize the amount of light. Okay, so we had this guy right here. So what I'm going to do is I'm going to play around with the variables a little bit. Give me 1 second. So if I move the variables around here, I have the following. I have the total amount of light is equal to, I can factor out I could factor out a 4. If I do that, I get a 4 down here. I'm going to leave the 4 here, but I can factor out the k, because that's just a number, and I can factor out the I2. So k I2 times, now here I'm going to have 4 over x squared plus 1 over 10 minus x quantity squared, just like that. Now what we want to do is we want to minimize this function, so let's go ahead and take the derivative of it. Now the thing is with this particular function in terms of x is that our x values are on the interval. X can only range from 0 to 10 because if you look at it, the maximum x can be would be 10, and that's if it was all the way over here, and the lowest it can be is 0, and that means if we were at a place all the way over here. Now we can only differentiate it on the open interval because we're not going to talk about left and right derivatives. So that's not a problem. Okay, so what we're going to do is we're going to find LT prime, or D. Another way of writing that would be to say we're going to find D LT with respect to x. So that would be equal to the derivative of this guy right here. Well, the derivative of this guy is ki sub 2 times, now the derivative of this right here, 4x to the negative 2, is going to be negative 8x to the negative 3. The derivative of this guy right here, well, that is 10 minus x to the negative 2. So that'll be negative 2, 10 minus x to the negative 3, okay, times negative 1, the derivative of the inside. So this will just be 2 over 10 minus x to the third power. So let's go ahead and put that up here. That's 2 over 10 minus x to the third power. Now if we look for its critical points, we set this guy equal to 0. So that means that for our x values, let me just rewrite this. This is going to be 2 over 10 minus x quantity to the third minus 8 over x to the third, like that. Clearly, if k is 0 or if I is 0, I2 is 0, then that's a solution. Okay, but these guys, we're assuming these guys aren't 0. Okay, so let's go ahead and play around with this right here. And so that'll give me the following. That'll give me 1 over 10 minus x 10 minus x to the third power is equal to 4 over x to the third power. So if we go ahead and we start working on solving this ugly mess right here, we get the following. We get x to the third should be equal to 4 times 10 minus x to the third power. So this is x to the third is equal to 4 times. This is going to be 100. Oop, not even 100. So it's going to be more than that. What we could do is use the fourth root, but I'll work this guy out. Okay, this isn't so bad. At least I don't think. Actually, it might be. Hang on one second. Here, I got a better way to do it. At this point right here, let's just take the third root of both sides. And the reason I'm going to do that, well, one, it doesn't matter whether x is positive or negative to take the third root. Okay, so the reason for that is because if x is negative, we'd have a third root, but if clearly x is not going to be negative, x is a positive value between 0 and 10. So this is just going to be x is equal to the third root of 4 times 10 minus x. And so this, if we go ahead and we play around with this a little bit, that'll be x is equal to 10 times the third root of 4 minus the third root of 4. Oops, third root of 4 times x. Just like that. So if we want to solve, get all the x's on one side. So that'll be x plus the third root of 4. X is equal to 10 times the third root of 4. Just like that. Okay. And so this would be x is equal to 10 times the third root of 4 over 1 plus the third root of 4. Just like that. Okay. So that tells us what the x value should be at the minimum. Okay. The other thing we should check is we should see if that actually is a minimum or a maximum, and also we should check to see what an x value of 0 gives us and what an x value of 10 gives us. So I'll do that in just a minute. Okay. But this right here for this x value, I'm going to get this in terms of a decimal. Okay, so it looks like the x value is about 6.14. Approximately. So if I take 10 minus that number, I get 3.86. And so if I go back up, this should be 6. What did I say it was? 6.14. And then this distance over here would be 3.86 approximately meters. Okay, so what it means is, since this guy is brighter, of course we'd expect it to be further down the line. Okay, so this distance is bigger than this distance right here. Okay, so if we wanted to go ahead and put our, there it is. Okay, so if we want to go ahead and put that guy in there, it's probably somewhere right about here. So this distance right here is this guy, and this distance right here is this guy. So it's closer to the less strong point source of light. Okay. Now that's probably the solution. Okay. So, but we should really check to see exactly what's going on there. Okay. So what we can do is we can take the following. We can take this guy, 6.14, and we can plug it back in to here. Okay. Well, this guy's just a number, so let's see. We want the biggest number we can out of here. So that'll be 4 divided by 6.14 squared plus 1 divided by the quantity of 10 minus 6.14 squared. And that gives us 0.17. Okay, so this guy gives us out 0.17 for the inside value. Okay, now if x is 0, well, x can't be exactly 0 because I've got this issue here, right? So if we go just a little bit to the side of it, we can calculate that term. Okay, so let's just do like point, I don't know, 0.0001. So let's go ahead and I'm going to calculate that guy out. Okay, so that would be 4 divided by 0.001 squared plus, well, actually, you know what? We can't actually calculate the end values. Well, we can calculate something close. Let's go ahead and see what we get out. And then I'll explain what I'm talking about in just a second here. So that gives us a number like 4 trillion? No, 400 million. Okay. So what happens here is we get some strange things if we plug in the numbers that are really close to these side guys. Okay. So clearly they're going to be more, though. The light's going to be more intense there than it is somewhere out here in the middle because they get extremely large. Okay, so now let's hang on a second. We'll go ahead and work on the next. Okay, so let's go ahead and work through this guy right here. So I'm going to take the derivative with respect to x on this. So I want dy with respect to x. The derivative of this with respect to x, because I can do each of these separately, the derivative of this is 2 times x minus a. Because the derivative of the inside is just 1 using the chain rule. The derivative of this guy is 2 times x minus b. The derivative of this guy is, you get the pattern. Oops, and so this last guy is 2 times x minus d, just like that. So in other words, dy dx is equal to 2 times the quantity x minus a plus x minus b plus x minus c plus x minus d. Or in other words, it's 2 times the quantity 4x's minus a minus b minus c and minus d. That's dy dx. Now the question is when is this guy equal to 0? Well, if I set it equal to 0, and I go ahead and solve, divide through by 2, not a big deal, I get 4x minus a minus b minus c minus d is still equal to 0. So 4x is equal to a plus c plus a plus b plus c plus d. So x is equal to a plus b plus c plus d over 4. Okay. Now, how do we know it's a minimum? Well, what we're going to go ahead and do is check the second derivative. So d squared y dx squared. Okay. And the second derivative with respect to x is just 8. And 8's positive. And so since 8's positive, that means that we're at a minimum where since this is positive, it means that the whole graph is concave up, which means that when we found the derivative at that point, it must have been at a minimum. Okay, just like that. So the number required to find the minimum is just the average or the mean. The mean. Okay, so this is just the mean of these data points. Okay, that easy. Okay, last one. So we've got the situation in both of these curves here, and what I'm going to do is I'm going to check these out. We're going to do this guy over here first. So to figure out this intersection point, what I need is the derivative of the first guy set equal to the derivative of the second guy. Oops. So 1 over 50x plus 10 equal to 50. Multiply everything by 50, I get x plus 500 is equal to 2500, just like that. And so x must be equal to 2000 days. Now let's quickly just check to see if that works as well over here. So if, actually it's going to be a lot harder to solve that guy. Let's, well not, I guess it's not so bad. So we would have x squared over 10, excuse me, over 100 plus 10x is equal to 50x. So x squared plus 1000x is equal to 5000x. So what we'll go ahead and we'll solve this. So we get x squared minus 4000x is equal to 0. So this means x times, let's see here, x times, you know what, actually that doesn't work. And the reason for that, oh, okay, I can tell you the reason why. These cost curves, okay, we need them to have the same slope. So we can't just set the cost curves equal to each other. We have to look at the slopes being equal to each other, because the slopes tell us the rate of change, how much is it costing us per day for the car, because the bus is in per day as well. So my fault on this first part, you can't set these guys equal to each other. You have to set their derivatives equal to one another.